The example we have is figuring out the pH of oxalic acid. Here is the equilibrium equation. We would have hydrogens and we would have the oxalate ion. But notice it's two hydrogens producing the oxalate ion. This would be the diprotic acid or polyprotic acid. On page 689, you'll want to flip to that because this is where you will find the values, the Ka and Kb values for some polyprotic acids. And you'll notice that oxalic acid is on there. It has a Ka1 equivalent to 6.5 times 10 to the negative second. It has a Ka2 that is equal to 6.1 times 10 to the negative fifth. Every case that you see on this table, the first proton comes off relatively easy. The second and sometimes third, where it's applicable, does not. So another way of saying this is that the second and third dissociation reactions are generally so far to the left that we can neglect them. The beauty of this is that most polyprotic acid pH problems then reduce to finding the pH from a single dominant equation. So as you work your examples in your text and your own problems, you'll see that the problem solving strategy is essentially the same to what we've been doing before. Instead of writing it the way I have done here to show the two hydrogen ions, we are going to look at it as if it is stripping these hydrogens off one by one. So the Ka1 would be for this equation instead. So this would represent the Ka1 6.5 times 10 to the negative 2. Now the Ka2 would be represented by taking the hydrogenated oxalate ion and pulling off the second hydrogen ion and then getting the final oxalate ion. That's how you would represent the two Ka1 and 2s that you see in the chart on page 689. From here, we're going to proceed similarly to what we did before. I'm going to rewrite the first equation here. So H2C2O4. So we're going to take the first equation with the Ka1 value of 6.5 times 10 to the negative second. And we'll do an ice chart like we have done before. So originally, the initial concentration for this one is 1.4. We have none of these. So you guys should be getting really used to this. Probably can do this in your sleep. So to write it out, it would be 6.5 times 10 to the negative second x squared over 1.40 minus x. If you go ahead and calculate the x using the assumption that the minus x here is a very, very small change, you get 0.302. If you check that number, 0.302, against the 1.40 to see if it satisfies the 25 or the 5% rule, it actually comes out to 21.5%. So this assumption does not work. So we will have to go back and calculate this equation using the quadratic equation. So when you get all your math complete for this, you get a quadratic, oops, it's not a minus. Minus 0.091. Use the quadratic equation, your x value comes out to 0.271. This is molarity, and of course this would be both the hydrogen ion concentration and also the hydrogenated oxalate ion here. So both of those. We can also calculate the H2C2O4 concentration by going back and plugging in the X value for the equilibrium of the oxalic acid. So this would be 1.183 molar. Now, if you wanted, you could go ahead and calculate the pH. So then back to the hydrogen ion concentration, the negative log of the 0.271, and it becomes 0.57. Now, that is just getting to the first hydrogen being pulled off. Notice the question. Let's go back up because I actually need to fix some things here. So here it should say oxalic acid. So we want to know that concentration. We want to know that HC2O4 concentration. And we need the H concentration. So we're looking for all of the species concentrations here, just for good practice. So far we have, let's see, we have this one, we have this one, and we have this one. So we need to get the C2O4 and the OH concentration. So how do we do that? Well, so far we've just taken off one H. So if we start with the product here, because we know that concentration, and we pull off another hydrogen to get to the oxalate ion, then we will have the oxalate ion's concentration eventually. Remember, this is for the Ka2 of 6.1 times 10 to the negative fifth from that table. And let's just see what we know. So we know that this is 0.271. We know the hydrogen ion concentration is 0.271. We don't know the X or the C2O4, so that's going to be our X. So here we can just plug in what we know for the equilibrium expression, products 0.271 times X over reactants 0.271. Mathematically, the 0.271s cancel each other out, and you're left with an X of, which is also the C2O4, remember. and that is 6.1 times 10 to the negative fifth. Notice this is the Ka2 value, which tells us that the C2O4 is not a contributing factor to the hydrogen ion concentration here. So we can go back to figure out the POH. Remember, is 14 minus the pH, which is up here, 0.57. That is 13.43. And then to find the OH concentration, we would do 10 to the negative 13.43. And I'm not sure. Oh, yes, I did. 3.7 times 10 to the negative 14th is the OH. So now I've figured out all of the species of my equation, concentrations of, and so forth. So because of this Ka value here, concentration being equivalent to the Ka value, this tells us that the first acid was the most important factor in our equilibrium. So when you're working problems, that's a valid assumption that the first acid is going to be the most important in the dissociation equilibrium. Okay, let's look at an example of phosphoric acid, which, remember, phosphoric acid fits this discussion because it has 3 hydrogens for every acid molecule. So if you look at page 689, you will notice phosphoric acid is at the top. It has 3 Ka values. So you're going to start with the first equilibrium reaction, which is going to pull off 1 hydrogen and leave behind dihydrogen phosphate. Oops, it's a 1, sorry. The Ka value, according to your textbook, is 7.5 times 10 to the negative third. So do an ice chart, but to simplify that work, we know it's going to be the Ka is products, both of which we don't know, so x squared, over reactants, which the phosphoric acid is 6 molar. When we calculate that, we get 2.12 molar. And if we check the assumption, 0.212 over 6 times 100, it comes out to 3.5. So your assumption's okay. This is going to be equal to both the hydrogen ions, again, and also equal to the concentration of the dihydrogen phosphate ion. We can go to the next. So we're going to take the product H2 PO4, which we now know, and we can break that down further into hydrogen plus now the hydrogen phosphate ion. The Ka value for this, according to your textbook, is 6.2 times 10 to the negative 8. So again, 6.2 times 10 to the negative 8. Products. Of the products, we know the hydrogen ion concentration is 2.12. We don't know the HPO4 concentration, so that will be an unknown value. We know the reactants, H2PO4 minus, the hydrogen, dihydrogen phosphate. So again, we have a mathematical, oops, I wrote that wrong. It should be 2.12. That cancels out. So the HPO4 concentration is 6.2 times 10 to the negative 8, which is again equal to its equilibrium concentration, or equilibrium constant. We can go one more step because there's one more hydrogen to pull off, HPO4 minus 2. So we have an H plus and a PO4 minus 3 this time. The Ka value here, even smaller, 4.8 times 10 to the negative 13th. Again, we found that in your textbook. So plugging in the numbers that we have and know, we know the hydrogen ion concentration, it's still 2.12. We don't know the PO4. The HPO4 was 6.2 times 10 to the negative 8. And when we calculate that, we get 1.4 times 10 to the negative 19th. I'm not putting my molarities in here. There we go. So it also asks us to find the hydrogen or hydroxide ion concentration. So here's where the Kw comes into play. Remember, Kw is hydrogen ion concentration times hydroxide ion concentration. We know the Kw for water is 10 to the negative 14th. We know the hydrogen ion concentration is 2.12. We're looking for the hydroxide concentration. So it's 1 times 10 to the negative 14th over 2.12 equals the hydroxide ion concentration. And when you calculate that, you end up with 4.7 times 10 to the negative 14th.